Light does something very strange. A photon, a little lump of light, always travels at the same speed, always. We call it c, the speed of light, about 186,000 miles per second. You can't speed it up. You can't slow it down. And here's the really crazy part. You can never bring a photon to rest. Never. You can't grab it and hold it still. It doesn't exist in that state. Think about what that means for a second. If something has mass, rest mass, we define that mass as the energy it has when it's sitting still. That's what E equals mc squared is really about. The energy something has just by existing, just by sitting there. But a photon is never sitting there. It's never at rest. So when you ask, what's the rest mass of a photon? You're asking a meaningless question. It's like asking, what's the marital status of the number 7? The question doesn't apply. Now let me show you why this is connected to the idea that light doesn't really move in the way you think it moves. When we talk about the mass of something moving, we have this beautiful equation from relativity. E squared equals p squared c squared plus m squared c to the 4th. That's energy, momentum, and mass all related together. For a photon, the mass is 0, gone. So the equation becomes simply E equals pc. Energy equals momentum times the speed of light. What does that tell us? It tells us that a photon is pure energy and momentum, nothing else. There's no stuff there, no substance. It's not a little ball flying through space. It's more like, well, let me think of how to put this. It's a quantum of the electromagnetic field, a ripple, a disturbance. And this disturbance doesn't move through space the way a baseball moves through space. The disturbance is the space doing something. Let me give you another way to think about it. When you throw a ball, the ball is one thing, and the space it moves through is another thing. The ball could stop, and the space would still be there. But a photon isn't separate from the field it's a part of. It's an excitation of that field. When we say light moves from point A to point B, what we really mean is that the electromagnetic field is doing something, and we observe this something at point A, and then we observe it at point B. Now here's where quantum mechanics makes this even more interesting. In quantum mechanics, we don't say the photon took this path or that path. No, we have to consider all possible paths. Every possible way the photon could get from A to B. Some paths are longer, some are shorter, some are completely crazy, going around the moon and back, and we add up the probability amplitudes, these little arrows that represent each path, and we get the final probability of finding the photon at B. What does this mean? It means the photon doesn't have a trajectory in the classical sense. It doesn't move along a line like a bullet. It's spread out over all possible paths at once until you detect it. And when you detect it, when you interact with it, poof, there it is. You find it at a location, but it didn't travel there by going from here to there in a straight line. It took all paths, or it took no particular path. The way we talk about it depends on what we're trying to calculate. Now, somebody might say, well, Professor Feynman, that's just math. That's just a trick for doing calculations. Surely the photon really does something. And I have to tell you honestly, nature doesn't care what you think it should do. The mathematics of quantum mechanics describes nature with incredible accuracy, the most accurate theory we have. And the mathematics says the photon doesn't have a definite path. So we have to give up our intuition about what moving means. Let me tell you something else that's peculiar. According to the photon itself, if a photon could have a perspective, if it could carry a little clock with it, no time would pass at all. From the photon's point of view, the moment it's created and the moment it's absorbed are the same moment. There is no journey. There is no passage of time. The photon doesn't experience motion because it doesn't experience time. This is what relativity tells us. As something approaches the speed of light, time slows down for it relative to someone watching. At exactly the speed of light, time stops completely. So a photon traveling from the sun to your eye, which takes 8 minutes by our clocks, by Earth time takes 0 time by the photon's clock. The photon doesn't age. It doesn't change. It doesn't move through time. So when I say light doesn't move, I mean it doesn't move the way you think motion works. Motion, as we understand it from everyday life, involves an object with mass that exists continuously as it goes from one place to another, taking time to get there. And we can imagine it going faster or slower or stopping. But a photon has no mass. It must always move at c. It takes all paths simultaneously. And from its own frame of reference, it doesn't experience the journey at all. Now you might ask, well then what is happening when I see light travel across the room? What you're seeing is a manifestation of the electromagnetic field. The field is everywhere. It's always there. And when we disturb that field, when we create a photon, we're creating a quantum of excitation that propagates through the field according to very specific rules. The rules of quantum electrodynamics, QED. And these rules are strange, very strange. For instance, when a photon bounces off a mirror, you might think it hits the mirror and bounces back, like a ball off a wall. But no, the photon could be absorbed and re-emitted by any atom in the mirror, or it could reflect from the front surface, or from the back surface, or from somewhere in between. All of these possibilities happen simultaneously in the quantum mechanical description, and we have to add up the amplitudes for all of them to get the right answer for where the photon ends up. This is what makes quantum electrodynamics so successful and so weird. We give up the idea of the photon as a little particle following a definite path, and instead we treat it as a quantum mechanical amplitude that can do anything allowed by the laws of physics. And somehow, when we add up all these possibilities correctly, we get the right prediction for what we'll observe. Let me give you another example, the famous double-slit experiment. You shoot photons, one at a time, at a screen with two slits. If you don't look at which slit the photon goes through, you get an interference pattern. Bands of light and dark. This means the photon went through both slits, not one or the other, both. The amplitude for going through slit A interferes with the amplitude for going through slit B, and you get the pattern. But if you put a detector at each slit to see which way the photon goes, the interference pattern disappears. Now the photon goes through one slit or the other, not both. Why? Because when you detect it, when you interact with it and determine which slit it went through, you've changed the quantum state. You've collapsed the wave function, as we say. You've forced the photon to choose a path. This tells us something profound. The photon doesn't have a path until you force it to have one, until you measure it. Before the measurement, it's in a superposition of all possible paths. And this isn't just a matter of our ignorance. It's not that the photon really went through one slit and we just don't know which one. No. The photon really was in a superposition of both. The interference pattern proves it. So what does all this mean for the idea that light doesn't move? It means that our everyday concept of motion, of an object going from here to there along a path, doesn't apply to photons. Photons are quantum objects. They're described by wave functions. They exist in superpositions. They don't have trajectories in the classical sense. And yet we still say light travels at the speed of light. We measure it. We get a number, 219,792, 458 meters per second, exact. So something is happening, right? Yes, something is happening. The electromagnetic field is propagating a disturbance, and that disturbance moves at speed c. But the photon isn't a little ball riding along on that disturbance. The photon is the disturbance. Now let me tell you about virtual photons, because this makes the story even stranger. When two electrons repel each other, we say they exchange virtual photons. These are photons that exist only in the intermediate stages of a calculation. They're never detected. They can't be detected. They don't obey the usual relationship between energy and momentum that real photons obey. They're off-mass shell, as we say. Virtual photons can travel faster than light, or slower, or they can go backwards in time. And this is perfectly fine in the mathematics of quantum field theory. In fact, we need these virtual photons to calculate the electromagnetic force correctly. The force between two charged particles is mediated by the exchange of an infinite number of virtual photons. And when we add them all up using Feynman diagrams, we get the right answer. We get Coulomb's law. But do virtual photons really exist? Well, they exist in the mathematics. They're terms in an equation. Whether they exist in nature as independent things, I don't know. Nobody knows. They're a useful way of thinking about the calculation, but don't get too attached to them as real objects flying back and forth. They're more like bookkeeping devices. And this brings me back to the main point. Photons, real and virtual, are not like baseballs. They're not like anything in your everyday experience. They're quantum mechanical entities that behave according to rules that seem completely crazy when you first encounter them, but which describe nature perfectly. When I say light doesn't move, I'm trying to break you out of the habit of thinking about photons as little particles that zip from place to place. Instead, think of them as quanta of the electromagnetic field. Think of them as probability amplitudes that propagate according to quantum mechanical rules. Think of them as disturbances in a universal field that fills all of space. And remember, from the photon's own perspective, if it could have one, it doesn't move at all. It exists at the moment of creation and the moment of absorption simultaneously. There is no in-between time for the photon. We, as outside observers, see the photon traveling from A to B at speed c, taking time to get there. But the photon itself experiences no passage of time, no journey, no motion. This is one of the deepest mysteries of quantum mechanics and relativity combined. We have these two great theories, and they both work beautifully, and they both tell us that our everyday intuitions about how the world works are wrong at a fundamental level. Photons don't move the way we think things move. They don't have mass. They don't have trajectories. They exist in superpositions of all possible states until we force them, by measurement, to be in one particular state. And yet, despite all this strangeness, we can predict what photons will do with incredible precision. We can design lasers and fiber optic cables and solar cells and all sorts of technology that depends on understanding exactly how photons behave. We may not be able to visualize it properly. We may not have a good intuitive picture of what's really going on, but we have the mathematics, and the mathematics works. So, does light move? Well, if by move you mean does something change from one place to another, yes. If you mean does it take time by our clocks for light to get from the sun to the earth, yes. But if you mean does a photon move the way a baseball moves, with a definite path and a continuous existence in time as it travels from here to there, then no, absolutely not. The photon is something stranger and more wonderful than that. Nature, at its most fundamental level, is not made of stuff moving around. It's made of fields and quantum excitations of those fields and probabilities and amplitudes and superpositions. And when we look closely, when we do the experiments and work out the mathematics, we find that our ordinary language, our everyday concepts like motion and position and path, don't quite apply anymore. This is what makes physics so fascinating and so frustrating at the same time. We're trying to describe nature, but the words we have, the concepts we've developed from everyday experience, they're not quite right for the job. We have to stretch them or replace them with mathematics, or sometimes just admit that we can't really picture what's going on, but we can calculate it, and the calculations agree with experiment. And that, to me, is the most beautiful thing. Nature doesn't care about our intuitions. Nature doesn't care if we can picture it or not. Nature does what it does according to its own rules, and our job as physicists is to figure out those rules and describe them as accurately as we can, even if the description sounds crazy, even if it violates everything we think we know about how the world should work. So the next time you turn on a light or see a beam of sunlight streaming through a window, remember, those photons aren't moving the way you think they're moving. They're doing something much stranger, much more subtle, much more quantum mechanical. And if that bothers you, if that seems impossible or ridiculous, well, tough. That's how nature works. And it's absolutely wonderful.